Indrek and Kadri, nice to have you here in the Unitartutech podcast, and you have published a cool paper. I will just let you two explain in detail what you discovered and achieved.
Yeah, thanks for having us. So we had this great publication and great work on spiders, or like that was inspired by spiders. So we look at how we can use materials to create robots. So to have the robot's body be the source of intelligence for the functions of the robot. And we looked at specifically spiders, and because like looking at what there is in the nature in living organisms can be a great way to like learn and see where you can go to. And we looked at how the exoskeletons of spiders are enabled by the internal liquid that's contained within.
And your findings?
Yeah, hi from my side as well. We found out that spiders are very different from what we conventionally consider robots as. And in many terms, they're also much simpler than we think. When you think of a robot, like a spider-inspired robot, we may think of thousands of small motors and very complex algorithms, which can be done as well, and there are robots, spider-inspired robots of that complexity as well, and very useful ones. But we were looking at to mimic the natural spiders in a bit of a higher level. And it turned out there are some aspects that we learned from spiders. They're pretty simple and also very powerful for also the roboticists. And in particular, the exoskeleton is for us nothing else than a container. Just all the spider is bounded by a cover that's termed exoskeleton that just contains the internal liquid. And it's a single liquid and a single container, so not much different than this cup here. And all the spider does is just to pump this liquid throughout its body, and the very same liquid also performs a large number of tasks in the spider's body. And also, well, we didn't make a full spider, we just made one joint of one leg of a spider robot. But nevertheless, the simplicity was what was striking to us.
So actually it is already in the scale of a spider. So spiders range from below 1 millimeter, like the spread of the legs, until like a couple of tens of centimeters in the tarantulas. And our like joint size, I think the leg was around 5 millimeters, 5 to 10 millimeters. So it's in the average scale of spiders. So something you can find in your own garden probably. But scaling up, I think what is most interesting for us is the technology, or how this liquid is used throughout in multiple functions. So because this is something that's really exciting, that's in all living creatures, but we don't really use in robotics or technology. So this multi-functionality of this single continuum of the liquid that's everywhere around the body of the spider in our work. But in the future, it would be that we would have this robot that has this one continuum liquid that is able to convey energy and information and like building blocks of the robots. And the like main beneficiary of this is that you can get the reaches everywhere. The reach is total. Right now, you would specifically need to take the like electrical wire or whatever piping or whatever mode of transport you have, and specifically deliver from A to B. And you have to be very specific, but with this liquid you could be everywhere at the same time, and then create specificity, like so you can like choose the concrete point or specific point you want to reach with like the chemical or like the composition of the liquid. So that would be very exciting to see.
Okay, that's fascinating. When I think of data transfer in such a liquid form in an organism, I would have to ask what exactly is the information in that sense. What are you emitting in that liquid?
Yeah, we are considering the information in quite in broad terms. More typically we consider like electrical way of signaling to activate some functions, for example, some muscular groups, and to transmit sensory data. Yes, a liquid does that as well. But it's what is interesting is that it's not limited to that one, or even more importantly, it achieves such information transfer in a much broader timescale. For example, also in our circulatory system, there is also a very slow, very long time frame signal occurring, which is driven by hormones. That is also a chemical way of signaling, transmitting information, also throughout the whole body and reacting to where it is needed. And the nervous system is also there, but specialized in fast reaction. When we need faster reaction, then hormones can enable. Also in our system, we have also artificial muscle there that performs slightly faster timescale actions, and it also is able to transmit chemical information in a broader timescale. People are so much fascinated on how fast you can make it, how fast we can make the spider. But I would ask how slow you can make a spider. See, in some applications, just to combine the longer term but still very accurate processes, that may be more important.
Would you like have to imitate some sort of sodium potassium pump type of interactions, and we had to play with pressure in some sense and with concentration of molecules? And
there are so many combinations you can use, like just taking inspiration from like biology or what is there in the living organisms right now. Like as Indrek mentioned, there's like hormones that can be very specific to the recipient. That's based on the cell wall. But we can create these sort of systems or in the robots as well. Right, so we can artificially create these kind of locking pairs, and it could be based on either biomolecules or it can be purely inorganic chemistry. So just the correct combination of salts and ions can react in one part of the body with one like specific electrode and not with another, and something like this. So there's like I think there's so much research that has these like discrete elements, but like combining them together is I think one of the next tasks. I think like finding the correct suitable cocktail of this internal liquid.
So it would be like a step towards organism that would have like a polymer based brain and blood plasma. Like in humans, it would have some ionic liquid that would enable all these functions and like be complementary. Like with enzymes in humans, you would have some elements that would suit each other.
Yeah, I guess that's just a quick note before you can answer. Like I guess that's the like exciting part of bio-inspiration. You can be inspired by biology, but you don't have to imitate it. So we can like use the technical knowledge we have and use like electric motors and stuff like that, but also use the combinations that are actively used in biological creatures, like the biomolecules. And so we can like mix and match however we want to, basically. Yeah.
Mm-hmm. Yeah, that you mentioned, it was very good that you mentioned sodium and potassium, that are the active parts in our bodies. And one of the advantages of this bio-inspired design and the liquid enabledness, we could use also the same as active ingredients of robots. If it is just convenient for us, but one side is, as already mentioned, we can design the blood. We don't have we don't have to follow the natural template exactly. We can adjust, but still, that the ability to, in principle, use the exact same biomolecules as in natural blood, that gives us safety. That's very important in robots. So in safety, in robot safety these days, well, yes, it's a big thing also today, but we mostly consider aspects like self-driving cars do not ride on humans, yeah, something like that, or AI-related threats. Well, but when you go to a chemical side, why not to make also full robot embodiments chemically safe, so that they could probably eaten or decomposed later in the end of the life cycle of a robot. And you may notice I'm using also the term life cycle for a robot, so that the robot, as we incorporate more features, more characteristics from natural organisms, it also acquires more and more unexpected qualities. So we see that, really, it's not as simple anymore that we manufacture a robot and then we program the robot and then it works and then it is discarded or maybe recycled. But we think that the robots may also develop at least aspects of life. For example, they can develop instead of being manufactured to shape.
Okay, as I understand, they would the principles of evolution would apply with robots to some extent if the scientists were willing to adapt the most logical procedures and happenings from nature in the development.
Yeah, well, indeed, evolution is, as I also previously mentioned, the breadth of the timescales involved is also important for us. So that's also not excluded at all. But even within the lifetime of a single robot, or let's say a single individual, we could consider a particular robot. They could also evolve to a specific task or a change in the task. If it is required to be more flexible, such as a robot spider moving to a different terrain where it needs to be more compliant to the terrain, it may just need to be more flexible and not only to change the stiffness of one joint, but overall the body should conform better to the specific environment. How to do it this today? Well, yes, sure, it can be also tuned with the control algorithms, but at the same time, taking a look at the single liquid approach of the spider-inspired robot, it's a single liquid. The single liquid can also contain or condition the exoskeleton. as it has access to all parts of the body, it also can condition the whole robot, the whole robot's body simultaneously. That's much simpler.
How would you see these single liquid robots? Where would you see them perform?
The trick or the approach we have in identifying the scope of potential use is to look at the spiders, where the spiders are more effective than the robots we know today, that we, at least for common people, well, it's still quite a constrained set of robots that come that get into mind, like maybe self-driving cars, maybe something at the conveyors at factories, warehouses. Our robots, spiders, could perform better on streets. Well, not really. It's not really a fair competition. It's the existing solution is almost very good already. But when you look at the spiders, they excel in task areas that is currently almost not populated with robots at all. No existing examples of robots so far, or a very limited amount. And one of them is movement in unstructured environments, in complex terrains. Well, in economic terms, this is agriculture. Moving in very complex natural terrains to harvest something, to plant something, to just observe the natural ecosystem. But also spiders are very good in crawling into different crevices. So another very prospective application is finding survivors in earthquake situations where it just needs very spider-like agility. Yeah. So that spiders spider robots could perform there better. But as you mentioned, the military, yes, of course, being able to move cameras and microphones where we would like to, but others not noticing is well, it's inherent as well.
Produce a bunch of killer spiders and send them to the front lines. No, that would raise some ethical boundaries, definitely. The rescue robot application, harsh construction sites that have really high risk of injury for human workers.
Yeah, there's actually so many environments that are not particularly inviting for people. Disaster sites, some very difficult to reach, like locations in nature, all of these locations.
But the production lines where you use radiation, when we go into sci-fi for a minute, I don't know what your favorite sci-fi movies are, but I remember Elysium, where this guy gets a really high dose of radiation because he gets locked in a chamber where these basically robots are produced.
Well, the production aspect is, let's say, quite with a small twist. So again, comparing to the inherent abilities of organisms and robots, there are many manufacturing tasks that are already outperformed and way outperformed by industrial robots. For example, you could assemble a mobile phone with a robot, maybe 100 times faster. I don't know, but it's a very large number times faster and more repeatable way than any human would be able to do it. But why it's performing very well in that particular application? Because that's a very designed, controlled environment where the phone is assembled. And one of the challenges is coping with the uncertainty, the variability of conditions. And if it is the manufacturing and agriculture meet, and for example, the robot needs to be manipulating with extremely various, very complex shaped objects, like fruit, some produce. The task gets more and more complex, and well, yes, sure, it can be solved also. Also in the control systems approach, sure.
Like
However,
plucking with drones or something.
Well, the drone in itself could also contain, let's say, a spider-inspired grippers that actually interact physically with the object we would like to pick or test the quality. So it's more. We don't have to make the full set of spider. So we could also only imitate one leg of a spider, and to also make very practical robots. The rest can be a conventional drone.
How many doctoral students would you need to build spiders for some big agricultural company or some harvesting company?
Let's say leg by leg or joint by joint for a full spider.
So one joint equals one PhD student. Each spider leg has 7 joints, and you have 8 legs. So
yeah, I like that math.
56, or what is it? No.
Yeah, 8 legs. We should have picked insects that have less legs.
Yeah.
But actually, talking about applied projects, still there are a number of applications much closer in time scale, sometimes a bit neglected, but still of high value that can make our lives easier. And what we are doing currently is simulation training. Mannequins that currently are not really lifelike, and as our core of research is making robots more lifelike. Well, why not also introduce this knowledge there? It's a bit simpler technologically, because it doesn't have to jump and run on an open field. It's okay if it is just sitting on a table of a trainer, instructor in a teaching setting, and it just performs all the magic of human physiology. Yeah, so that you can see the process, not only the shape of it, but the full process of it. So technologically, it's much more approachable, and the impact is still huge for our life quality in terms of better training for medical or healthcare personnel.
How much of an impact potential do you think this freshly published paper holds in itself? Shake the boundaries of soft robotics once and for all.
Absolutely. This is our work, of course, we believe the most of it, right? So we have to believe in our work to make good work, I guess. But I think it's an interesting perspective that's not really viewed, and you never know if it's going to be revolutionary or not. So, but I think it's definitely adding a lot, and like seeing how much discussion in the community there is about using, like, how to get powering for your robot, and the liquid is a good way of getting this powered, this embodied in that energy concept. It's beginning to, like, you see more and more of it these days in publications, but it's not really something that anybody has solved. So I think, I don't know, it's difficult questions to say, like, yes, in 5 years it will be like 5,000 publications per year on this topic. No, we can't say that. Mm-hmm. But hope for the best, I guess.
Yeah, the scientific frontier is quite unexpected. It could push the frontier to in quite unexpected areas. That and the energy containment of the liquid is something almost not solved. It is being considered, but still no one really knows how to solve it efficiently. The idea is to have a full embodiment, the robot's body, to also contain energy for its operation. And again, when you think of the spiders, animals, also most of their body contains energy in its different forms. So we could think of, let's say, a comparison to some battery-driven robots these days. Well, batteries, I think, almost exclusively contain also liquids. But we conventionally neglect that. It's just some battery chemistry that happens. Okay, and now we start counting in an electric car how many individual cells we have to make up the whole electric car battery. Each of them contain one individual liquid container, which each need to be isolated from each other and from the environment. It's quite a complex engineering. So the idea of embodied energy is that in the same analog to electric cars, it would be fully contained by a single liquid, and the liquid would also, let's say, carry the energy needed. So a single element, single component in the machine performs many tasks simultaneously.
And in this single liquid, have you already explored the possible candidates for like this energy transmission or synthesis? Like in humans, we have like adenosine 3-phosphate by the ATP, where the energy gets produced in cells, and are there similar molecules with functionalities that you would imagine would suit?
That's our next research project, actually.
Yeah.
So coming soon, hopefully. But yeah, I think there's like, you can pick and choose. I think there's lots of options. You have to just find the one that suits your system best. You can, for example, just take the conventional battery liquids and technologies, like the electrodes and the materials used there, just decompose them into that full body of the robot is filled with that same battery liquid. And then, like, in concrete points that you want to take the energy out of this liquid, you have those pairs of electrodes, for example. But or flow batteries, or I think there's quite many possible, like.
So in different regions, you would have like electrodic currents.
That would be like an interesting like concept to see, because like in organisms you have blood that carries like in humans you have oxygen that is carried around. That's the main thing where you get the energy from in each individual cell. So I guess we would imagine maybe something similar, that you had this continuum liquid that's flowing around, and then in specific points where you want to take this energy out, like in the cells, where you want the cells to use this oxygen to.
So the transporter of this energy source would be complementary with the energy carrying part, and it would also itself be manipulated by some electrocurrent or something like that.
No, for example, that's like the beauty of having this correct cocktail, I think, that you could have the same liquid that carries these functional particles for energy, for embodied energy, to carry the energy all around the organism. It could also have like other like ions or biomolecules or all sorts of things that could have simultaneously different functions or different tasks. So on one hand, you want to power the full robot, but at the same time, you might want to deliver information from one leg to the other, for example, from arm to the other, right? So you could all like have it in the same highway, basically, and see if that makes it better.
The same general task to make robots more agile, more capable, it's solved in quite a number of approaches, different methods. So we belong to, I think, to a minority, at least in the field, who are approaching it from completely bottom up to synthesize robots in a chem lab. Yeah, normally you would see more, let's say, roboticists working on programs implemented on some hardware platforms. Well, we do coding as well, but the code is the composition of the liquid and the shape of the robot.
The materials.
And the materials chosen to construct the embodiment.
I guess in a sense, like if you're talking about benchmarking, what is there in the community? There's maybe some work that have like considered liquid as like a way of conveying energy throughout the body of the robot, but not too many, and they didn't have like exciting result in the sense of conventional benchmarking, like what's the speed of the robot, what are the actuation speed of the robot, and how many cycles can it perform, and what's the reliability, and I think these are like maybe topics we might need to refine a bit, especially because you don't really ask that.
And Indrek, you mentioned life cycle, right?
Yeah.
That robots have a life cycle.
About benchmarking, main benchmark for us is the nature, of course. At least this is a very specific comparison. So how close we could mimic some aspect. Well, if it is a target in its own right, we could also, of course, adjust the target. But still, it's some benchmark that is also frequently used elsewhere, just in bio-inspired robots, how close we can implement some aspects. And a specific example from the spider study is how much force we would need for the spider leg joint to exert. So, more conventional benchmark will be okay. We take some high power actuators and benchmark for the highest force produced, which will give some result. However, we found even a much more powerful approach is to compare the power or the force output to the natural spider legs. And we found out that the spiders, in their activity, even if they are escaping, do not need to exert more than a few body masses of load to their legs. But still, we can see they are very fast in escaping. So the force requirement for this spider robot is actually quite moderate, much more moderate than we would think beforehand. And when we made the comparison, it looked like if we would implement in-scale body for this robotic spider joint, we would have sufficient force. So a great benchmark, just it worked very well in our study just to have force output per body weight as a benchmark.
just like nature intended, and it's already optimized.
Yeah,
The power output and input
yeah.
ratio.
I guess it kind of translates that you have to understand the environment, and based on the environment and the task, you benchmark it. And like taking some numbers that we know already from biological research is helpful. But just like the important part is understanding the task and the environment, and not just what else has been done in a sense. Because with this soft robotic solution or physical intelligence, we're aiming towards these kind of robots or embodiments that are able to switch tasks or switch environments with the same tasks. So you have a wider variety of what you can do without like reprogramming or rebuilding your robot. So it's not about what's the maximum torque or what's the maximum force. It's what is it like successful in completing the task or not. Because it like at the moment I think there's not really good parameters how to like objectively describe all the tasks you can do, because there's billions of them. Like even like picking up something on the street versus in like a hilly area, it's different. Or like walking in a straight line on the street is very different from, I don't know, walking uphill or hiking. So all these things are, I think we can consider them as different tasks in a way. So because the environment is different and the situation is different.
Extracting a plutonium rod in a,
yeah, it's different.
Power plant.
Yeah.
Or picking pollen. That was the case study also in our paper.
Yeah. Like how do you pick like a small bunch of pollen grains that are like micrometer? Or,
the force requirement is not that much of an issue at all.
Yeah.
It would require a really small scale Spidey.
Yeah.
And
the compliance, so you won't
gather the pollen, right?
Yeah.
So then the agricultural perspective comes in again. So not only to pick the fruits, but also to pollinate. Yeah?
This is absolutely amazing. I mean, you guys single-handedly took Einstein's words to heart, and when we're going to lose the bees, then in 5 years we will be extinct. So you guys maybe can make it to 25 years when we have tiny spideys pollinating flowers.
Yeah, hopefully the bees survive.
But it's actually really at some point when the fertilizers get more and more used, and we push the volumes of agriculture up, and we use Roundup and stuff like that, and glyphosates to get rid of the weeds, right? So then the bugs that pollinate, they eventually die out, and we are forced to create another method to keep the ecosystem in balance.
Yeah.
So that's a wonderful application that it could inhabit. Yeah. Possibly. Mind blown on my side. Cool. At this point, I think the viewers are also amazed at how much a little spidey leg can bring hope and promise to the world through the hands of and brains of scientists. So I thank you guys for joining us today.
Thanks for inviting.
Thank you.